Fine. Before going into the first problem, we'll find out the ways and means to calculate the natural frequency, because we have lots of method like simple harmonic motion, Newton's law of motion, energy method, Rayleigh method, D'Alembert's principle and all those stuff. Right now we are going to concentrate mainly upon one particular method which is used to solve about 90% of vibration problem, which is energy method. Okay, so we'll see what an energy method is. So energy method is used to solve any kind of 90% of vibration problem. Okay, mostly you could be able to solve it using energy method. Once you are confident, once you are expert in this factor, you will be able to solve any problems very easily. Before going into this energy method, we'll see one particular system, because this can be applied only to the system where the energy is conserved. Okay, only where energy is conserved, only where energy, for example, no kind of energy should be lost during the process. Okay, so that's the prime important thing while applying a energy method. Then we have two important energy involved in this. One is kinetic energy, which is a function of velocity, because we know kinetic energy, formula for kinetic energy is half mv square. And then we have potential energy, which is a function of displacement, because we know the energy stored in the spring is half kx square. So we'll let you know about it in the coming time. So now we have this energy method. One more important thing to know is, like, we'll have to have some thermodynamic concept to understand this also. If you are aware of this point and path functions in thermodynamics, work and heat are path functions because it has to trace the path it goes through, right? But pressure pressure, temperatures, all those are point functions. Now so now we have this spring energy, which is a point function, which means it is conserved. So spring force, so for example, I'll say one equation, I'll write it down, one equation. So potential energy 1 to 2 can be written as kx, this is spring force, into dx, which is distance from x1 to x2. If I could just derive it, so minus, for example, if it's compressive, okay, so minus k x2 squared by 2 plus, since it's minus, it will become plus x1 2 squared by 2. So this is the thing. So since it depends upon 2 points, okay, energy's total system is dependent upon 2 points, 1 and 2. So we can call this to be a point function. Okay, one important stuff we have gone through, and next we'll directly go into the concept. Now we'll see methods, how to solve, the method to solve using this particular concept, energy method. So first we'll have to find total energy of the system. What are the energies involved? It might be rotational kinetic energy, it might be linear kinetic energy, it might be spring force stored in the energy, spring energy stored, and all those stuff. So first we should find total energy. Then this total energy, for example, if it's E, differentiate E with respect to time should be 0. This is the main principle which has been conveyed using this energy method. So this is what we are going to use as of now for almost all the concepts. Right now in this tutorial we are going to use only this, and after this you are going to be an expert in solving any kind of vibration problem using this energy method. So first is, we'll see the first example, first problem 1. Problem 1, it's very easy, very simple, basic spring mass system. We have K, we have M, right? So it has a displacement in x direction. I'm going to pull it and I'm going to leave it off. Okay, so let's say I'm going to have a fixed support over here. I'm going to have it over here. So this is the displacement x, it has gone through, and I'm going to leave it. It's going to be in a vibratory motion. So what is going to be the time period, or what is going to be the frequency in 1 second, how many oscillations does it goes through, and all those stuff you are going to see. It's very simple. First, if you could see the system, what are the energies involved? Just see for energy while it is in a rotary motion. Since it's moving up and down, we can be very obvious that it's going to have a moving energy, which is a kinetic force, which is linear. So kinetic energy linear, it's going to be half mv square. Fine, very easy. Next, the energy is potential energy of the spring energy. So spring energy, which we have only one spring, so spring energy is equal to force, which is kx, into distance. So it's going to be half kx squared. So this is what is a spring energy. So we have even a smaller kind of derivation for it, since it's obvious and it's going to be 7th standard, 8th standard physics, or even if you can study this in +1. So I'm not going to go into this derivation, but if you are interested, let me know in my description. I'll be able to come up with derivation in a separate video for it, because I can't deviate from the particular topic. So this is half k square for the spring energy stored in the energy stored in the spring. Now what am I going to do is I'm going to have total energy. What is total energy? All the energies involved in the system should be, just add up all kinetic energy. So we have linear kinetic energy over here as well as spring energy. So spring energy now, so E equal to K half mv squared plus spring energy is half kx squared. So one more important thing to know is this is a single degree of freedom. Single degree of freedom means it has allowed to move only in one direction, and that's what been shown over here, because calculation is very easy while we assume it to be a single degree of freedom system. So while we go into the process, I'll let you know the difference between a single degree of freedom, a double degree of freedom, a triple degree of freedom, and all those stuff. Right now this is single degree of freedom, but we have a velocity over here, we have a displacement x over here. So we need to have it in a single degree of freedom, single variable, and all those stuff. We know very well v is equal to dx by dt. Okay, display change in place with respect to change in time. So change of place with respect to dx by dt, and dx by dt can also be denoted by x dot. And as far as this is concerned, I could write one more thing: acceleration is equal to d squared x by dt squared, double differentiation of x variable with respect to time, which is equal to dv by dt. This is very simple. I could write it as x double dot. Okay, so fine, we have two important stuff to keep it in our mind. Now we know very well v is x dot. I am going to just write it down as just half m v square is x dot squared. Okay, now plus half kx squared. So this is very easy. Now this is E, just differentiate E with respect to t. Since this is already differentiated, which is dx by dt, we could easily differentiate it again. So half m, so substitution method, 2x dot into x double dot plus half kx squared is 2x. Okay, it's going to be very easy. 2x into x dot, sorry, since it is with respect to time. Okay, now this is done. So just solve this. Since it is equal to 0, I am going to solve this. 2 cancels. I could take x dot as common values outside, mx dot plus kx equal to 0. So x dot is common, I could take the other side and gets cancelled. So final answer, I could have it as mx double dot plus kx equal to 0. So this is of simple harmonic motion equation. What is simple harmonic motion equation? So x double dot, I could just rewrite it as one more step, x double dot plus k by mx equal to 0. Simple harmonic motion equation goes like x double dot plus omega n squared x equal to 0. So if you could see, we could take out omega n squared is equal to k by m. So omega n is equal to root of k by m. So once, it might be a difficult thing for you as of now, but once you start to practice, once you go ahead with many problems, you could solve this as easy as that. It's going to be really simple. Now, so we have got an angular frequency which is root of k by m. Okay, so we have got it. Now we'll go on to more complicated problems, but we'll solve this using the same energy method. We'll see in the next question.